So, how does a service with hundreds of millions of users, one of the fastest growing in history by the way, run its entire operation? You'd probably think it's some kind of futuristic, custom-built database. Well, today, we're going to uncover the surprisingly simple and frankly downright shocking answer. First, let's just let that number sink in for a second. 800 million users. That is just a staggering number of people, generating an unbelievable amount of traffic and data day in and day out. So, the big question is, what kind of crazy, hyper-complex database architecture does it take to handle that kind of load? I bet you're picturing a massive, globally distributed, totally custom system, right? Well, the reality is kind of unbelievable. At the very heart of it all is a single primary database. Yep, you heard that right. One main instance of Postgres handles every single write operation for this entire global service. So how on earth is that even possible? This really is ChatGPT's big secret. Instead of building something brand new, OpenAI's strategy was to take a classic, trusted database and just push it to its absolute breaking point limits. So here's the basic setup. They use one primary PostgreSQL server on Azure for all the writes. Simple enough. Then, to handle the massive number of people reading data and getting responses, they have nearly 50 read replicas scattered all over the globe. This thing is already handling millions of queries a second. And get this, its load has grown over 10 times in just the last year. I mean, it's a classic strategy, but the scale is just off the charts.
But, a simple design like this isn't bulletproof. As ChatGPT's growth went from just rapid to absolutely meteoric, the cracks in this architecture really started to show, and some pretty serious vulnerabilities came to light.
They actually found themselves stuck in this really nasty, vicious cycle. Okay, so picture this. Something simple goes wrong, like a cache somewhere fails. That causes a sudden spike in database queries. This makes latency shoot up, so requests start to time out. And what do users and services do? They retry, of course, which only amplifies the load, and boom, the whole system spirals towards a total meltdown. Now, a big piece of this puzzle is a core PostgreSQL feature called MVCC. It's fantastic for letting lots of people read and write at the same time, but it's got this hidden cost. Every time you update even a tiny piece of data, it copies the entire row. So during a big surge of writes, you get this huge write amplification effect, which can slow that primary database down to a crawl.
All right, so with all this chaos, what do? Well, the OpenAI team developed a multi-layered strategy. This wasn't about finding one magic fix, but a whole series of clever engineering solutions to tame this beast. First up, they tackled the classic noisy neighbor problem. They basically isolated their workloads, splitting traffic into high-priority stuff, like your actual ChatGPT prompts, and low-priority things, like background jobs or new features. Each of those gets its own dedicated database instances. That way, a traffic spike from some new, unoptimized feature can't bring the whole house down for everyone.
Okay, next up was a huge fix, connection speed. See, opening a new connection to a database is actually pretty slow. So they brought in a tool called PgBouncer to create a connection pool. Instead of every single request opening a brand new connection, they just get reused. And wow, the results were dramatic. The average connection time dropped from 50 milliseconds all the way down to just 5. That prevents these connection storms and just makes everything way faster.
But they didn't stop there. They threw a whole toolbox of other optimizations at this thing. They hunted down expensive queries, including this one absolute monster that was joining 12 different tables. Yikes. For tasks with tons of writes, they started moving that work over to a different database, Azure Cosmos DB. They also built a super clever cache locking system. If the cache misses, only one request gets to go to the database, which prevents a stampede of thousands of identical requests. And of course, they layered in rate limiting everywhere to keep traffic spikes in check.
But wait, what about that single primary database? Isn't that a massive single point of failure? Good question. To deal with that, they run it in a high availability mode. They've always got a hot standby replica, just sitting there, perfectly in sync, ready to take over in an instant if the primary database hiccups. This makes failovers super fast and keeps downtime to an absolute minimum. Even something as routine as changing the database structure, the schema, became a huge deal. One seemingly small change could lock up and rewrite an entire massive table. So they had to lay down the law. Only lightweight changes are allowed, and they absolutely must complete in under 5 seconds. No exceptions. So when you kind of step back and look at the big picture, you can see it clearly. For every single major challenge they faced,
From write inefficiency to the risk of the primary failing, they engineered a specific, targeted solution. It's this incredibly comprehensive approach that creates stability at such a mind-boggling scale.
Okay, so all that hard work, did it actually pay off? Let's look at the results, because the numbers here are pretty wild.
First up, availability. They hit 5 nines. That's 99.999% uptime in production. I mean, that is an insane standard of reliability for any service, let alone one operating at this scale and growing this fast. And what about speed? Did they have to sacrifice performance? Nope. Their P99 client-side latency, which means 99% of all requests are faster than this, is consistently in the low double-digit milliseconds. It's not just up, it's fast. But maybe the most telling statistic of all is this quote, straight from their engineering blog. In an entire year of just explosive growth, they've had only one critical Sev0 incident, that's the highest severity level possible, related to Postgres. Just one. And what caused that single incident? Get this, it was a new feature that went so viral, it brought in over 100 million new users in a single week. That caused a sudden 10-fold surge in write traffic. It literally took an event of that magnitude to finally stress the system. But, of course, the work is never really done, right? With growth still on a ridiculously steep curve, they're already looking ahead, planning for the next phase of scaling, on the road to 1 billion users and beyond.
So here's what the road ahead looks like. Today, they have that primary server feeding data directly to all 50 or so replicas. Pretty soon, they're going to move to what's called cascading replication, where replicas start feeding other replicas, kind of like a chain. That'll let them scale to hundreds of replicas without crushing the primary. And long-term, they're finally looking at sharding PostgreSQL itself.
So what are the big takeaways from all this? First, never underestimate the power of tried and true tech. They push PostgreSQL to absolutely incredible new limits. Second, there's no magic bullet. Stability at this scale comes from a multi-layered defense. And finally, you can't just react to problems. You have to be proactive with your engineering to stay ahead of exponential growth.
And that leaves us with one last big question to chew on. OpenAI managed to break through the database wall for 800 million users. But as AI continues its march toward 1 billion users and way beyond, what do you think the next great engineering bottleneck will be? Thanks for watching.